video, we've talked about the properties of Fourier transforms, including linearity, time shift. That is, if you shift the signal in time by a certain interval, then the magnitude of the Fourier transform stays unaltered. There is no change in the magnitude response as a function of frequency. However, in the phase, you have to add omega t naught, okay, t naught being the interval by which the signal is shifted in time, okay. So it's just the multiplication of the exponential by the Fourier transform, that is the time shifting. Then we talked of conjugate symmetry, that is if you have a real signal, then its Fourier transform is conjugate symmetric, and as a consequence of this statement, let's say if xt is both real and even, then your Fourier transform is also going to be both real and an even function in omega. That is, you don't need to consider the Fourier transform for negative values of omega. I mean, the positive values of omega are sufficient to display the frequency content, because that's what you are going to have on the negative side of the frequency axis. So for an even signal, the Fourier transform is both real and even, okay, function of omega. If it is odd, if the signal is odd, then Fourier transform is purely imaginary and it's odd, okay. So these are the things that we discussed. So let's continue with the next properties. So next is the differentiation and integration. So so you see, if you have a signal xt, let xt be a signal with Fourier transform xj omega, then differentiating both sides of the Fourier transform integral, if you take the first differential of xt, okay, so both on the right hand side and the left hand side, you see the integrand takes the form of j omega xj omega, okay. So what does this equation implies? Okay, this equation is not synthesizing xt back, but instead it is giving you d by dt of xt, the first differential of xt. So that means the Fourier inverse of j omega xj omega is dxt by dt. That's the first differential of the signal. So this implies that the first differential of xt, taking the first derivative of the signal xt, has a Fourier pair j omega xj omega. Okay, and this is quite evident from the Fourier synthesis equation, or the inverse Fourier integral. Okay, the inverse of not xj omega, inverse of xj omega is xt. Okay, but j omega xj omega is going to give you dxt by dt. Similarly, this is the forward transform and this is the reverse transform. So these are the Fourier pairs, right? Okay, so this is particularly an important property, as it replaces the operation of differentiation in time domain with that of multiplication of j omega in the frequency domain. So if you are going to differentiate your signal in time domain, in frequency domain it means multiplying the transform with j omega. Okay. Now, since differentiation in the time domain corresponds to the multiplication of j omega in the frequency domain, one might conclude that the integration should involve the division by j omega in the frequency domain. Well, that's indeed the case, but you see, that's only one part of the picture. Okay, why? Because you see, integrating a signal might return you a constant or a DC value. Okay, and if you recall a signal, which is you recall that the signal is not absolutely integrable. Okay, if it is absolutely integrable, then the Fourier transform, it is sufficient condition to show that the Fourier transform exists. Either it is absolutely integrable, or you say that okay, the energy of the signal is finite. The Fourier transform exists, and this is a sufficient condition to show that the Fourier transform exists. If this is not the case, then signal xt is going to violate the Dirichlet condition, and in that case there are signals, for example xt is ut, xt equal to ut. For example, if it is a step function, for step function you will see in Fourier transform tables, the Fourier transform does exist, and it exists in terms of delta functions. You will have delta functions not in the time, in the frequency domain, right? So for such signals which are neither absolutely integrable, neither they have the finite energy like u of t. Okay, so from 0 to infinity you can go ahead and have a finite convergent integral. Okay, this be 1, and I mean the absolute value of ut is 1, right? So dt 0 to infinity is infinity, right? So it doesn't obey Dirichlet's condition, but it doesn't mean that the Fourier transform doesn't exist. It does exist in terms of delta function. So the idea is that integration might involve a DC or a constant value. Okay, the result of integration of a signal might involve a DC value. So in transform domain, you have to admit delta functions for that. So the impulse on the right hand side of the equation reflects the DC or the average value that can be that can result from the integration. Okay, so it's not only 1 over j omega times x j omega like we had in the differentiation. In integration, um, you will have the multiplication by 1 over j omega and then a delta function. Okay, I mean, for example, if you have to recover, if I take the differential of both sides, okay, of the signal, then that should imply in the Fourier domain the multiplication of the entire term with j omega, right? And you will see that you're going to recover x j omega only, okay, because this the left hand side will be x of t, right? I mean, if you take the differential, that will be x of t, and the Fourier pair will be this will imply the multiplication with j omega. So the first term is x j omega. The second term will be plus j omega by x of 0 delta omega. Okay, so you see the thing is that x of 0 in frequency domain, this is a constant. Okay, pi is a constant, j is imaginary number. What is omega delta omega? Omega delta omega is 0, right? Because delta function is only existent at omega equal to 0, otherwise it's non-existent. So this is 0, right? And at 0, well, if you're going to multiply this with 0, it's 0. So this implies that this whole thing goes to 0. So you're left with xt has a Fourier xt is Fourier paired with xj omega, which is the consequence of taking the derivative. So this integration property holds valid. Okay, I mean the Fourier pair that results after integrating a signal xt will involve a delta function, given that if the result is containing any DC or the average value. Okay, let's take some examples to concretize our understanding on differentiation integration. So this is example 4.11 from your course text, and it says let us determine the Fourier transform x j omega of a unit step function, okay, ut, and you will see that ut, as I was said earlier, ut is neither absolutely integrable, neither it has a finite energy, but it does has a Fourier transform, and the Fourier transform will exist in terms of delta functions, okay, because it does not obey Dirichlet's conditions. So it will have all the signals which do not obey Dirichlet's condition, they will have delta functions, okay. An example is an exponential, that is a growing exponential, for example. And you recall that in Fourier series, we did consider the Fourier transform of exponential in terms of delta functions, okay. So all those functions which do not have finite energy or they are not absolutely integrable expect delta function in their Fourier transforms. You can show this by taking inverse Fourier transform. That's an easy way to show that such functions pair with the delta functions in frequency domain. Okay. So anyways, let's get back to the example. So it says let us determine the Fourier transform x j omega of the unit step function, making use of equation 432 and the knowledge that, okay, this is from the text. Basically 432 is this equation. Okay, in text this is 432 in Oppenheim and Shepherd. Okay, let's start with the gt, and we know that if gt is delta t, it has a Fourier transform of 1, right? I mean, that means that all the frequencies are contributing equally. Delta t is a Fourier transform of 1, that's an elementary Fourier pair. So noting that xt can be, since xt is ut, so how do you make express xt using g of t? Well, you have to integrate delta function from minus infinity to t, and basically this is your u of t, right? So now we know that what is g of j omega, and we also know that integrating a signal xt, for example, xt from minus infinity to, let's say, t. Okay, well, this is the dummy variable tau over here, then d tau is x j omega. Since if we know what is the Fourier transform of xt, then we can use this for the integration evaluation. If the signal is integrated, then this is x j omega divided by j omega plus pi x0. This will be pi x0 multiplied by delta function. Delta function is delta of omega. That's it. Okay. So again, this second term on the right hand side of the equation is as a result of DC or any average value occurring from the result of integration. So taking the Fourier transform on both sides, well, this is the case that we have over here in terms of g omega. Okay, so we know that delta function is the Fourier transform of 1. And if we take the Fourier transform of considering this equation for x j omega, then this is the integration. Okay, so this becomes g j omega, just like over here, g j omega over j omega plus pi g of 0 delta omega. Okay, and so we have used this integration property, which is listed in table 4.1 of the text. So since g j omega is 1, so substituting this value in the above relation, okay, g j omega is 1, so x j omega is 1 over j omega plus pi delta omega. Okay, I mean g j omega is 1, g of omega is 1 for all omega. Okay, so g of 0 is unity, of course. So well, that's your Fourier transform. This is basically the Fourier transform of ut, right? I mean, you can also say that this is the Fourier transform of ut. So you notice that ut, which doesn't obey the Dirichlet's condition, which is neither absolutely integrable, neither it has a finite energy, its Fourier transform does exist, and it exists in terms of the delta functions. Okay. So you observe that if we apply the differentiation property to reverse the integration effects and to recover the transform of the impulse, well, if you have to do that, you know that d by dt of ut is your delta function, right? I mean, that's what this equation is saying. I mean, if you take the differential of both sides, you have gt, right? And gt is delta function precisely. This is your delta t. So if you have to do that, then in the transform you have to multiply both the left hand side and the right hand side by j omega, right? So if you multiply both sides by j omega, then the first term is unity, right? And the second term is 0. Why? Because omega delta omega is 0. Okay, so this term is going to be 0, right? Because of multiplication with omega over here, the second term. So all you have is 1. Okay, so I mean, this is the transform of ut, and if you take the derivative in the time domain, which will lead you to delta t, in the transform domain it means multiplication with j omega, right? So in the transform domain you are left with unity, right? And this unit represents the Fourier transform of delta function precisely, right? So this is how you use this derivative or integration in the transform domain. These properties are very handy in evaluating functions which could be more complicated than unit step or delta functions. For example, this next example 4.12, gives quite an unorthodox sort of a function, g of t, which is d by dt of xt. Well, xt, as you see, is sort of a triangular function, okay, on both sides. So suppose that we wish to calculate the Fourier transform x j omega for xt, for the signal xt, which is displayed in figure 416a. This is 416a. So the signal xt for which the Fourier transform is to be evaluated in this example. So rather than applying the Fourier integral directly to xt, we instead consider the signal dx by dt. Okay, so part B of the figure represents the derivative of xt as the sum of two components. You see, if you take the derivative, this rising slope has a constant gradient, so we'll have a rectangular waveform shape like this, and then on the extreme ends there will be impulses, right? So basically dxt by dt can be bifurcated into two signals. So the one part is where you have this a constant gradient. Okay, so derivative of dx by dt is positive, the gradient is positive, and then you will have and you can see this gradient is 1. Okay, this is 1. I mean, this function is from -1 to +1, -1 to +1, xt is t, right? Xt is t, so derivative dt by dt is 1. But at ±1, where there are abrupt jump discontinuities, we'll have delta functions. Okay, so what is Gj of omega? Let's see if we can write this by linearity. You can go ahead and write the Fourier transform. If you recall from your past examples of 4.4, well, the delta functions which exist from, let's say, minus t1 to plus t1, and sort of this. I think we considered this in 4.4. You recall that the Fourier transform was a sinc function, right? It was a sinc function. So the expression for such a function was twice, if this is xj omega, if this is xj omega, this is 0, and then this is 1. So x of j omega was of the form twice sine of omega t1 divided by omega, which it's a sinc function. So if you relate this Fourier pair for this the first rectangular signal as a first decomposition of the derivative of xt, you can write the g omega as twice sine of omega, twice sine of omega divided by omega. So this is because t1 is 1, right? So plus, what about the impulse, right? You know that for delta function, we have seen in the previous example as well, delta t has the Fourier pair of 1, right? And if it is shifted in time, let's say it is shifted by plus minus 1 at both sides, which is the case over here, right? It is shifted by minus 1 at plus 1, then that implies the multiplication of 1 with e of minus j omega, and basically this is plus minus j omega 1, right? So you will have basically this will be minus e of minus j omega, because there's a minus 1 over here, right? The strength is minus 1 and it's shifted by minus 1. Then again the strength is minus 1, but it is shifted by 1 at plus 1, so this is plus j omega, right? I mean, this is the Fourier transform of gj omega. You see the same thing over here. So you see, as illustrated in figure 416b, gt is the sum of rectangular pulse and two impulses. The Fourier transform of each of these component signals, they may be determined from table 4.2. So all we have done is to relate the Fourier transform of a rectangular pulse with the sinc function, and we've used this with the linearity, that since the derivative of the function, I mean, instead of plugging xt directly into the Fourier integral and finding this Fourier transform out, we have make ourselves comfortable. We have done the analysis in a much easier way by using the differentiation property and then using linearity property, that if we know the Fourier transforms of two signals, and since it is composing the differential of xt, we can combine them. And you also notice that d by dxt, so basically this is nothing but j omega. I mean, taking the derivative of xt implies that in transform domain this is nothing but j omega x of j omega, right? So g of j omega and x of j omega are related to each other by direct multiplication of j omega, okay, by multiplication factor j omega. So you can find xj omega from this expression. Xj omega, if you have to do this directly, will be equal to twice sine omega divided by j omega squared, okay? And well, instead of writing those exponentials again, what we can do is we can combine these two exponentials, right, into a cosine function. So it will be minus twice cosine omega divided by j omega. That's it. This is your this is the Fourier transform of xt, right? I mean, we have not used the Fourier integral for that. I mean, if you had to do that, then you have to model this impulse over here, this discontinuity in the function, and there are three regions to for Fourier integration. You have to model at t equal to -1. You have to consider the Fourier integral at the discontinuity is t equal to plus -1, and then you have to consider the region between minus and plus -1, that is t. I mean, that would have involved some mathematical complexity, but considering its derivative, and we know that taking the derivative of xt simply means j omega x j omega, and we know what is the Fourier transform of rectangular pulses, and we know what is the Fourier transform of delta functions are, which are shifted in time. It's easy. We can relate x j omega to the differential by simply dividing the right hand side of capital G j omega, which is the Fourier transform of the derivative. Dividing this by j omega gives you x j omega. Okay, so this is quite straightforward if the derivative property is employed. Okay, so this is one of the utility of such properties, that it eases the analysis. So, so you see, we have the same expression of f(x j omega) over here as well. So the other way around is if you have to use, for example, okay, what we did is we said that, okay, since this is the derivative of xt, which is j omega x j omega, to recover xt, we can also use the integration property. I mean, you take the integral of both sides, then this will give you xt, right? With respect to, if you take the integration with respect to time, and this is xt, and then you could have employed the you can use the integration property like this over here. So this is what is has been done, but these both are the same alternates. So if you use the integration property and implying g j omega, you have the same expression, and you know that g0 and delta omega, the multiplication is 0 in the first place because g0 is 0, right? I mean, look at g0. G0 is, for example, it's 2 minus 2, right? So ej0 is 1, ej0 is 1, so 2 minus 2 is 0. So again, you will have the same thing. With g0 equal to 0, this becomes twice sine omega over j omega square minus twice cosine omega because of this term divided by j omega. Okay, so you can do it either way. Either you can use the integration property, or you can argue that, okay, this differential is j omega x j omega, and you can divide both sides by j omega to get x j omega. Now, another interesting fact to note is that xt or this signal is odd, right? I mean, this is equal to minus x of minus t, right? Which means what? Which means that the Fourier transform will be purely imaginary and odd. Okay, that means that, so the first thing to note over here is that the real part of your x j omega is going to be 0. That is, Fourier transform is purely imaginary, it doesn't have any real part to it. Okay, and which is the case over here. Look at x j omega. This is your x j omega, right? So this is purely imaginary. Both the terms are consisting of j, right? And it's an odd function. Why? Because sine function is an odd function. Well, cosine function is an even function, but there is omega in the denominator, which makes the second term is odd as well, right? So the first term is odd, second term is odd, x j omega is odd. So if the function is real and odd, the Fourier transform is also odd, okay? And it's purely imaginary. That is, x j omega is minus x of minus j omega. So this is another property that is being that is valid for this Fourier transform of xt. Okay. So the expression of x j omega is purely imaginary and odd, but is consistent with the fact that xt is both real and odd. Okay. All right, this brings us to the next important property, that is time and frequency scaling. So what it says is that if xt has a Fourier pair with capital X of j omega, then if you scale the time by some number which is real and positive, then the Fourier pair of it will be 1 over modulus of a x j omega by a. It simply means that, for example, if a is a positive quantity, that means there is a compression in time. Okay, so the compression in time will imply expansion in frequency. It's just like if a sinusoidal signal is, I mean, if you go on increasing the time period in frequency domain, it means that the fundamental frequency is decreasing, right? So it's as simple as that. So you see, a is a non-zero real number in this property. So this property follows directly from the definition of the Fourier transform specifically. Well, so if you have to show this, then you can say that, okay, the Fourier transform of xat is this function. Okay, so you plug this in the Fourier integral. This is the Fourier integral. And what you can do is from a little substitution of mathematical, you can do some mathematical artifice over here. You say that, okay, tau is a dummy variable, which is the scale version of time, t. This is at. So to bring this dummy variable tau over here, which is at, you have to divide this by a as well, the frequency. Okay, omega by a into at is the same expression. So omega by a tau. And this is for a greater than 0. For a less than 0, you will have a negative sign because a is less than 0. Okay, but in both these scenarios, you see the this is the scenario. This is the result. The Fourier pair. If you scale the Fourier pair is as such. If you scale the time by some positive real number, then the frequency is either it has to be scaled. It has to be rescaled. It either expands or decreases. Okay, so but there is a modulus of a as well that is coming, because either a can be positive or negative, so you have to consider the modulus of a over here depending on the sign of a, and that is shown over here, omega divided by a. So omega divided by a means this is the Fourier transform is not xj omega, it is xj omega by a. Okay, so this is the Fourier transform. Another interesting fact is that if you, for example, if I say that a is equal to -1, and that simply means the signal is time reversed. The signal is simply flipped over, and this flipping is done taking the vertical axis as the mirror. So it has a Fourier dual of x of -j omega. So this follows from the consequence of time scaling property. It means if you are going to flip your signal in time, it is also going to flip itself in the transform domain. The Fourier transform is also going to be flipped, so it is x of -j omega as a consequence of that. So thus aside the amplitude factor 1 over a modulus of omega, a linear scaling in time by a factor of a corresponds to a linear scaling in frequency by a factor 1 over a, right, and vice versa. So also letting a equal to -1, we see from the following equation that reversing the time, flipping the signal in time means flipping the transform in frequency over the frequency axis. So that's reversing the signal in time reverses the Fourier transform. That falls from the consequence of scaling. Intuitively, however, you illustrate is a common illustration of frequency scaling is the effect on the frequency content that results. For example, when an audio tape is recorded at one speed and played back at different speeds, you'll see that the frequency content is either scaled. By scaling, it means either the frequencies they expand or they contract. So, for example, if the playback speed is higher than the recording speed, correspond to the compression in time. For example, if A is higher, so if you're going to play your tape at twice t, right, then what does it mean? It means then the spectrum is going to expand in frequency. It will be, since 1 over 2 is just a multiplier, it's not it's just affect the amplitude of the frequencies. But what we are going to hear is not omega, but omega by 2, right? So this means there is a scaling. So if you scale the time by 2 in frequency, the frequency is scaled by 1 over 2, right? So this is what it says. A linear scaling in time by a factor of a corresponds to linear scaling of the frequency by 1 over a. So that's indeed the case. So the audible effect is that the playback frequencies are higher. Conversely, if the signal is played back with the scale down in frequency, so if the playback speed is slower than the recording speed, so if the recording speed is lower, if it is, for example, t by 2, then you will have x twice of omega. Okay, so I mean the idea is the same. The scaling property is another example of the inverse relationship between time and frequency. That is, if you increase the period, frequency decreases, fundamental frequency decreases. So, and we've already encoded this on several occasions. So for example, we have seen that if we increase the period of sinusoidal signal, we decrease its frequency. It's just like omega naught has an inverse relation with the time period. So as the time period increases, omega naught decreases. As t increases, omega naught decreases. Okay, so you see the scaling is multiplication by a over here, then the scaling is 1 over a over here, vice versa. Now another very important property is in Fourier transform pair is duality, and this is a consequence of the symmetry in the Fourier inverse integral and the Fourier forward integral, I mean, they are not exactly identical, but you must notice some symmetry in these relations. Okay, I mean, both has integrations and both involve exponentials, but for example, there's a change in sign over here and multiplication of 1 over 2 pi factor. There always exists a duality. That is, if capital X, if xt takes the form as capital X of omega, then the inverse Fourier transform will be small x of j omega. Okay, so let's try to understand the statement in detail. So what it says, by comparing the transform and inverse transform relations, we observe that these equations are similar, but not quite identical in the form. So this symmetry leads to the property of the Fourier transform referred to as duality. In example 4.5, we hinted to duality. Basically, if you recall in 4.5, we noted that relationship exists between the Fourier transform pairs, example 4.4 and 5. So if you revisit example 4.4, we saw that if xt is a rectangular pulse, then the Fourier transform is going to consist of a sinc function like this. And in example 4.5, we said the other way around, that if in the transform domain we have a rectangular pulse having a width of 2w, then the inverse Fourier transform is going to give you a sinc function. So sinc function and rectangular pulse are the Fourier duals, right? If you have a Fourier, if you have a rectangular pulse in time domain, in frequency domain it's a sinc function. If you have a sinc function in time domain, then the Fourier transform is a rectangular pulse. So these are the duals, right? These are the Fourier duals. So in the formal example, we derive the Fourier transform pair. So if you have xt as a rectangular pulse like this, the Fourier transform is a sinc function. If you have a sinc function in time domain, you have a rectangular pulse in transform domain. So this is duality, right? And this occurs because of a symmetry in the Fourier integral and the inverse Fourier transforms in these two equations. So this is depicted over here. So this figure is showing you the relationship between Fourier transform pairs, and these transform pairs are rectangular pulse and the sinc functions. So these are the Fourier duals. Okay. So specifically, because of the symmetry between Fourier integral and inverse Fourier equations, for any transform pair, there's a dual pair where time and frequency variable interchange. So if you interchange the frequency variables, I mean, for this, the frequency variable is omega. If you change this to t, then in transform domain, t changes to omega, and you have a rectangular pulse back. Okay, I mean the Fourier pairs or Fourier duals, they become Fourier duals if you interchange the variables, right? The variables are the frequency and time. So this example is again from your course text 413, shows the importance of this duality in evaluating the Fourier transforms. Let us consider using the duality to find the Fourier transform capital G of j omega of the signal gt. Gt is given as 2 over 1 plus t square. And you note that a few things to note from here is that gt is a real signal and it is even in time. This will imply that g of j omega, capital G of j omega, is also going to be both real and even. Okay, so what I can deduce from this information is that before, I mean, we don't know what the expression of g of j omega is. We're going to do that. We are going to find that in terms of the duality property. The g of j omega will be an even function and it will be real. Okay, so this will be a even function in omega. That's the first thing. And the second thing you are going to notice that it's going to be real. That is, the imaginary part of capital G of j omega is going to be 0. So these are the two things that I can just say by looking at the function and my interpretation in terms of the properties of Fourier transform. Well, you should be able to deduce this. That's what the properties are for. Okay, they make the analysis much simpler. Okay, let's continue with the duality. So in example 4.2, if you recall, we encountered a Fourier transform pair in which the Fourier transform as a function of omega had a form similar to that of xt. So specifically, we consider the signal xt whose Fourier transform is this, and it is very similar to the function gt, just that the variables are interchanged. Then from example 4.2, you also recall that this was a Fourier transform. It has a Fourier pair with e minus magnitude of t. So it's going to exist on both the sides, right? I mean, as t is increasing, it's like this. So this is e of minus t. This is 1 over here. Okay, probably this has to drop more like this. This is your e of minus t. This is 0. Okay, so these are the Fourier transform. You see, this signal is also both symmetric and real. So the Fourier transform is both real and even. So we know that for xt, this is a Fourier transform, right? So the synthesis equation for this Fourier transform pair is, in terms of the integration, xt is given by 1 over 2 pi. This is your x of j omega, right? If you plug this into the Fourier synthesis integral, then you have to multiply this with e j omega t. So you can bring the 2 pi to the other side, okay, and multiplying this equation by 2 pi, and then you go ahead and replace t by minus t. What happens is that there won't be any change on the left hand side, but the right hand side will be of the form minus infinity to plus infinity. The same integrand, okay, the integrand is going to involve, of course, omega. It's a function of omega. Multiply by e to the, if you're going to change t by plus t, that will be e of j omega t, right? Then d omega. So what is this? Well, this is the Fourier inverse. This becomes the inverse Fourier transform of what? This will be 2 pi e of minus t. 2 pi e of minus t. This becomes the inverse Fourier transform of, if you have to divide this by 1 or 2 pi, this becomes the inverse Fourier transform of e of minus magnitude of t, right? This is what it says. So now interchanging the names of the variables t and omega in the next step, you should find out that if you change the variables to omega changes to t, okay, and there's a change of variable over here as well. So there's a change of variable over here. This becomes 2 1 over t squared, okay, and what else? This becomes omega. This becomes omega, okay. So this is 2 pi e of minus omega. So minus infinity plus infinity. This is 2 1 plus t squared e minus j omega t. So this is basically this will be minus j omega t, and this becomes the Fourier transform of 2 over 1 plus t squared, and the Fourier transform is given on the left hand side, that is 2 pi e of minus omega. So the idea is that, okay, you have a signal, which in this case is 2 over 1 plus t squared, for which we do not know the transform, and in fact evaluating the Fourier transform directly with integration is not that straightforward. What you do is you imply duality to use. So you know what is the Fourier transform of e minus magnitude of t is 2 over 1 plus omega squared, right? So that means if you interchange the variables, if this becomes the function of time over here, then by the duality principle, the Fourier transform will be of the same form. It will be e of minus omega, right? Of course, there is a multiplication of 2 pi because of, to symmetrize the relationship, you have to multiply 2 pi on both sides, okay? So to make it a Fourier integral, you have to interchange the variables t and omega as well. So precisely or mathematically, this becomes the situation then. So you see that the left hand side gives you the transform, right? The result of this integration is this, and all we have done is to use the Fourier pair, the only Fourier pair, okay, that the only Fourier pair that we use is, we know that e minus a magnitude of t has a Fourier pair with 2 plus 1 over omega squared, and then you can use this duality relationship to find the Fourier transform of g of t, right? So the Fourier transform analysis equation for 2 plus 1 over t squared. So indeed, this is the Fourier transform of 2 over 1 plus t squared. That's it. Okay, we didn't have to go ahead and evaluate the Fourier integral for this function. We would have been lost in evaluating the integral and the mathematics involved. So you can use the duality principle to ease your analysis. So the duality property can also be used to determine or suggest other properties of Fourier transform. Specifically, if there are characteristics of function of time, they will have implications with regard to the Fourier transforms. Then the same characteristics associated with the function of frequency will have dual implications in time and in the time domain. what it means is, as an example, earlier we saw that the differentiation in time domain means multiplication with j omega corresponds to the multiplication of j omega in the frequency domain. Then from duality, from the preceding discussion on duality, we might then suspect that multiplication of jt in the time domain corresponds roughly to the differentiation in the frequency domain. Okay, and this is indeed the case. For example, if you consider the Fourier integral and take the derivative of both sides, take the derivative, this has to be multiplied. So the derivative is with respect to omega, and if you take the derivative of the exponential, it will be minus jt multiplying xt. And you note this, if you look at this equation closely, then the differential of the Fourier transform has to be paired with jt. Okay, that is, if you take the derivative in the transform domain, in time domain it's the multiplication with jt. Just like if you take the derivative of xt in time domain, you have to multiply the transform with j omega, right? So again, it's a linear multiplication in time domain with jt, provided you take the derivative in frequency domain. Okay. Similarly, the following dual properties can also be derived. For example, if there is a shift in frequency, then this should imply a Fourier dual, an exponential multiplication for the same factor e j omega naught t with the signal xt. Similarly, if you integrate in the frequency domain, then in the time domain it will be the multiplication with 1 over jt xt plus a delta function, which is not in the frequency but in the time domain, owing to any resulting dc or the average value as a result of the integration. Okay, that's all.